Hi everyone, welcome back. In this video we are going to talk about transformations of trigonometric functions. So, as we know that for all trigonometric functions, they're all periodic. So by saying periodic, that means if we draw the axes, the function graph, or the function itself, will be oscillating like this in some way. So let's say that we have a general trigonometric functions. Let's use sine as an example. So let's say we have an function such as y is equal to a sine times bracket b x minus c plus d. So if we have a sine function like this, what we will have is a few parameters here. We would have a, b, c, and z. So this is how this general function differs from a specific or a simpler form y is equal to sine x. So in this video we will explore what do these specific parameters mean and what are their functions specifically to this function right here. So specifically we can see that if we draw a graph for y for this general equation or function, we would have a function like this. Because it's a sine function, I will draw like this. So like this. So let's start from A. So A, we call A amplitude. That means it is denoting the max difference between the x-axis and the max on the y on the graph, or the min on the graph. So both of these are A's. So let's say I have a function such as y is equal to 2 sine x, then the max value of the graph would be 2, and the mean value of the graph would be negative 2. And we will intuitively see that A would simply be max minus min, which is the distance between the max value and the minimum value on the function, over 2. And the second one we're going to explore is B. So B is sometimes we call we will use B to find period, but B itself is not the period. So the period is the how much time or how much distance does the graph take to complete one full revolution. So for sine and cosine function, a period can be calculated as 2 pi over b, and for a tangent function, it will be equal to pi over b. And this b, we put a absolute value sign here. So this period would denote the distance from here to here. So this would be how much time or how much distance that the graph is taking to complete one full cycle, which is essentially from here to here to here. So this would be one full cycle. A full cycle could be regarded as from a crest to a crest, from a trough to a trough, or as I drew on the screen right here, like this. So usually, in order for a graph to go through a full cycle, it needs to experience at least a max and a min value for a sinusoidal function. The value c, as in mostly the same for other type of functions as well. If we have a constant applied directly to x, it would denote a horizontal shift. And in the context of a trigonometric function, we usually call this a phase shift. So imagine if we shift this whole graph slightly to the right, or maybe slightly to the left. So these three graphs, brown, green, and purple, they all have the same A, same B, same D. They just have different C. So C is essentially a horizontal shift or a phase shift along the x-axis, or a line that is parallel to x-axis. Now, last but not least, D. So D is also similar to other types of function. D denotes a vertical shift. So, for example, still, let me draw, if I shift the whole graph a bit upwards, or maybe I could do it downward movement, downward transformation. So they are all considered as a vertical shift, and the amount of shift could be reflected from the constant parameter d right here. So let's look at a example function, and let's try to identify all the specific informations associated with this function without actually drawing the graph. So our example would be y is equal to 3 sine x minus 2 plus 5. So let's go from one by one. The first thing that we should pay attention to would be a here. So as we know, a denotes amplitude, which is essentially the distance between either the max or the min and the x-axis. So this is saying that if we draw it along the x-axis, and if we have something like this value here would be 3, and this value here would be negative 3. Next value, negative 2. So we know that this would denotes a horizontal shift or a phase shift. And we know that for a horizontal shift, if it's moving to right, then it's a minus, and it's moving to left, it's a plus. So since it's a minus 2 here, it means that the whole graph is translated 2 units right, which is essentially saying it's something like this. And then the plus 5. So plus 5 denotes a vertical shift, and if it's moving up, it will be positive, and it's moving down, it's negative. So since it's a plus 5 here, it means that we are shifting the whole graph 5 units upwards. So the final graph will look like this, but this will be only a portion. And here, the b value would be 1, which is to say that the period would simply be 2 pi over 1, which is 2 pi. So the period for this function would be 2 pi. And since the trigonometric functions are always oscillating indefinitely, at least for a simple general sine function, cosine function, and tangent function, so realistically, or actually, the graphs are extending indefinitely like this. both ways. So that would be the way that we could go from a general function formula to the actual graph, or to all the specific information associated with the function without actually drawing out the graph. And the specific method is all listed here and here. So by examining these specific values and constants hidden in the actual function formula, we can figure out these different informations associated with a trigonometric function. Okay, I hope you find this video helpful, and thank you for watching. See you in the next video.